later. Okay. So it tells me to put 2 points on the polar graph. So I'm just gonna like make 2 random ones. I don't know, this one, and let's do this one. Why not? Right? And so let's make this P1. So that has distance R1, right? So that's R1. And this angle here is theta1. And then we have, maybe I'll do it in a different color. Then we have this guy here. I'll do my best to draw a straight line. Oh, on the tablet, it's so difficult. Oh, there we go. Okay. And this will have that length R2, and then this whole angle will be theta2. And we want, maybe I could do a line for this one. We want the distance between the 2 points, or this black line here. So how can we find that? Well, there's a nice little shape we have made. And what shape is that? A triangle. Is it necessarily any specific kind of triangle? No, right? Because I could have picked a point all the way down here and I'd have this like crazy triangle, right? It's not a right triangle. It could be. It could be isosceles. It could be scale. It could be anything, right? It could be a really weird looking triangle. That one almost looks like a right triangle, so I kind of don't like the points I picked. Maybe I'll like scoot my blue one over real quick, just so anyone taking notes doesn't like look on it later and be like, well, I thought it was right triangles. So let me do a point like, let me do something crazy, like all the way down here maybe. I don't want it to be the same distance away either, so maybe there. Then we can take this, right? Okay, maybe we'll do that. There we go. And then again, this is still that second distance, and this whole angle here is theta 2. And it does make a triangle, yes. And we want to find that distance. So let's see here. So we're going to pretend that we know both of these angles and both of these distances here. So how can I find this distance? Maybe I'll call it D. We have a triangle. Hold on. First question. This class has been about what? Like the entire thing. If you had to pick one thing about this class that we deal with, what is it? Trig. Yes. Trig, 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 trig. Yes. Okay. SOHCAHTOA can only be used on right triangles, which we don't necessarily have. There were 2 things we learned, and we kind of use them a little less, sometimes. There were 2 things we learned that we could do on triangles that weren't right triangles. What were those? Law of cosines, and then the other one, um, or I don't even remember which one he said. One, law of sines and law of cosines, right? Those 2 things we can use on triangles that are not right triangles. And that's exactly how we're going to find this distance. So, the angle we have here really, hold on, the angle of this triangle that we know right here isn't theta 2 or theta 1, but it's theta 2 minus theta 1, right? That is going to be this angle here. And then we know these distances, so we want to find D. Well, this is just the law of cosines, really, that we're going to use, if we remember it. And it says this side squared, D squared, equals one side squared, so r1 squared plus the other side squared minus 2 times r1 r2 cosine of the angle, which is theta 2 minus theta 1. And then, right, the actual distance would be if we took the square root, because we need to take the square root in order to get d by itself. So, really, d, once we do that, is going to be the square root of r1 squared plus r2 squared minus 2r1 r2 cosine of theta 2 minus theta 1. And this is probably something you want to have written down right here. The distance between 2 points on a polar graph is this. So if you want to label it, you probably don't have to write this top one, but this is going to be the distance between 2 polar points. We'll give you guys time to get that down. And that was just using the law of cosines on this triangle that it made. Okay. If you need me to go back, I can. So, for example, 5, surveying. Before large road construction projects or even the construction of a new home take place, should that be takes place, a surveyor maps out characteristics of the land. A surveyor uses a device called theodolite, I think is how you pronounce that, to measure angles. The precise locations of various land features are determined using distances and the angles measured with the theodolite. While mapping out a level site, a surveyor identifies a landmark 450 feet away and 30 degrees to the left, and another landmark 600 feet away and 50 degrees to the right. What is this? The distance between the two landmarks. By the way, if you go to college, at least the one I went to, you see these kids in their surveying class all over campus, freaking year round. They all have these. I'm assuming those little theodolites. I guess I should like Google it. You see them outside on campus all the time measuring stuff. Like you're just walking to class and they are measuring stuff all year round, constantly. Um, so this is definitely a real world thing. So let's do this. So all the important stuff is right here. While mapping out a level site, a surveyor identifies a landmark 450 feet away, and 30 degrees to the left. So I'm kind of thinking like I like to think of our like polar axis. The book kind of did it a different way, but if that's our polar axis, right, I want to think, okay, we have 450 feet away. I kind of drew it back to there, but it doesn't really matter. So this is 450 at 30 degrees, right, left of where he's looking, right? If you pretend you're kind of like sitting this way, looking, that's to the left. And then it says, and 600 feet, 50 degrees to the right. So a little bit wider of an angle and a longer line just to maybe make it look real. And then this is going to be 50 degrees to the right, but the actual angle isn't, right? The angle we want to deal with isn't, like this angle is going to be 50 degrees, but the actual angle we want to deal with is going to be 360 minus 50, or we could say negative 50. Personally, I like to always just deal. I don't like to deal with the negative angles. So I'm going to do 360 minus 50, right? I'm going to do this whole angle around, which is 310 degrees, right? 360 minus this 50 here, right? And so the distance between these 2 points, right? But I guess maybe negative 50 might be better for the calculator if you want to do that. I'm going to need my TI-84 app. So we should be able to do our distance between the 2 points is equal to the square root of, oh, and this was 600. 450 squared plus 600 squared minus 2 times 450 times 600 times the cosine of, and then you could use negative 50 here. It works either way, right? But I'm going to maybe do 310 minus 30. Which is 280, right? And so I'm just going to stick that in this calculator. All right, so the square root of 450 squared plus 600 squared minus, I'm going to put these in parentheses, 2 times 450 times 600 times the cosine of, what was it, 280, and I am in degree, so that should be good. And we get 684.6 feet. So why is this here doing lines? 684 point, and I have the memory of a goldfish. What was it? 6.6? Yeah. Point 6.